Okay, Assalamu alaikum. So today, inshallah, we continue the same chapter, which is heat transfer concept and properties of the material. So in this chapter, we have already covered 2 lectures. If you remember, in the first lecture, we talk about the radiation, the spectral power, which covered the spectral emissive power, the spectral irradiation, and the spectral radiosity. And we know the difference between each one of them. We said the emissive power is the power that emitted at a certain wavelength from the surface. The irradiation, we mean by it the power that incident on the radiation, and the radiosity mean that all the radiation that leaves the surface in terms of reflectivity, or in terms of reflection, reflected radiations and emitted radiation. Then we talk in the previous lecture about the properties of material. Mainly we talk about the reflectivity, absorptivity, transmittivity of the surface, and we talk about this within the spectral or within a certain wavelength. We introduce Kirchhoff law in the general form, which means that absorptivity equal to emissivity. This was the Kirchhoff law. Also, we said that all the surfaces can emit radiation when it is above 0 temperature. And the new thing we added within this lecture, that it depends on the wavelength, which means that if I have a surface such as this surface at a temperature, for example, 300 Kelvin, so normally it would emit radiation. However, this surface will not emit radiation unless it reaches more than 2 wavelengths. So we said that the emissivity is function in both the temperature, and it is depend on the wavelength. So we have to know the wavelength, because some of the surfaces cannot emit radiation if it's below a certain wavelength. Also, as I said, that we covered Kirchhoff law in the general form, and we use this form to make a relations between the reflectivity and absorptivity and the emissivity, or we can say between the spectral reflectivity, spectral absorptivity, and spectral emissivity. We use this form to find or to calculate the emittance and absorptance of the real surface. And we know that the real surface has less absorptivity and emissivity than the black body or the ideal surface. So to find these properties or these parameters, emittance and absorptions, we use these 2 relations, since we already divided by dividing the wavelength into a certain into small segment, and we make summations the emissivity to, I want to find the emissivity for a real surface, so I find the we make a summation for the multiplication of the emissivity at a certain wavelength time the fraction of the black body emitted from the surface. Why we use these relations? To find the both absorbance and or emittance and absorptance of the surface, and these both are as a function on the reflectivity. Why we do this? The only property that we can measure in the lab for the surface is the reflectivity. So depending on the Kirchhoff law and the relations between these 3 parameters, we can find the other properties with the emissivity and the absorptivity, and we already solved problems on this part. Also, we defined, or we said that the emissivity is a surface property, because any surface, as we said, can emit radiation at a certain, if it's at above 0 degree and depend on the wavelength. However, the absorptivity depend on the incident spectral radiation. So Here we find that the absorptivity depends on the spectral radiation, but the emissivity, it's a property of the surface or a surface property. Up to here, is it clear? Any questions until here? I want to start from this last point, which I said the emissivity is a surface property, while the absorptivity is depend on the incident radiation. Normally in the absorber, we try to find, or we want our surface to absorb maximum radiation and emit or loss less radiation. So this means I want to maximize the absorptivity and reduce the emission that will leave the surface. Mean that what is the radiation that will leave the surface? It's in terms of two parameters, in terms of reflections and in terms of emissions. Do you know, or I've already now defined the radiosity. What we define the radiosity? We said that the radiosity is the radiant energy leaving the surface in terms of reflection and emission. So we always try to minimize these two parts, the emission and the reflection from the surface, because these two parts considered as losses. If I have absorber, so these two parts, actually it is a losses. I want the surface to absorb all the radiation to increase the output, and to reduce the losses. Also say, if I define this one, I have to the radiosity in terms of equations. So this means that the radiosity G is, as we said, emissions and reflection. And if you remember, I said that the emissivity is a property of the surface. So emissivity multiplied by the emissive or spectral emissive power from the surface. However, the reflectivity, as you see in here, is depend on the incident radiation. So this is the surface, this is the incident radiation on the surface. Part of it, it will be, say, absorbed, and part of it, it will be reflected. So the reflected here is depend on what? On the incident radiation. So here we say radiosity equal to the emissivity of the surface, which we already know how to find it, times the emissive or black body emissive power, which is coming from the sun. The reflectivity of the surface, which we are going to measure it, time the incident radiation or irradiation, which we defined it before, irradiance. Okay, so this equation represents the total power or emissive power, total power that leaves, or total radiation that will leave the surface. This radiosity or this equation, actually, it is the concept of the selective surfaces. Why? Because I want to reduce these two parts. I want to reduce the emissivity or the emission from the surface, and I want to reduce the reflection or reflected radiation from the surface. So the selective surface is a surface that should have maximum absorptivity or maximum absorption and less radiation that emitted from the surface. How we do this one? If you know, if we compare, now I have here, so solar collector, as we said, must have high absorptance for radiation in solar energy spectrum. At the same time, they lose energy by reflectance. So these two, reflectance and emittance, I want to minimize them. If we see the surface, suppose that I have a surface at a temperature 400 Kelvin. This is my surface. The blue line here is at 400 Kelvin, which is 200 degrees centigrade at the ground. So this is my surface. and this surface will start to emit radiation. As we say, the emission depends on the wavelength. So it will start to emit radiation after, say, after 2 micrometer wavelength. So at the long wavelength, it will start to emit radiation. So if I make this surface after 2 micrometer, emit as less as I can, less emission. So that means I will reduce the losses by emission. Before this range, before say 2 or 3 micrometer, what will happen? The surface here, there is an incident radiation to it, and this incident radiation will come from the black body, for example, the sun here. And below this, so 2 or 3 micrometer, the sun will start to emit maximum of its radiation, which is already will be incident on the surface, and part of it will be reflected. So in this case, we will try to make this surface at less than this range or the short wavelength reflect as low as it possible. Again, the surface, when it is at long wavelength, I will try to make it emit as low as I can. However, when it's at short wavelength, I will try to make it reflect as low as I can. So below at short wavelength, the low reflectivity. At long wavelength, low emissivity. Why? As we defined the radicity, the reflected radiation depends on the incident radiation, which will come from the sun, and in this term or in this range, the sun will emit maximum power. So I don't want it to reflect whatever it's already taken. Because of that, in this one, I want less reflectivity. However, when we are at long wavelength, maybe the sun, okay, there is an emission from the sun, but it's not that much. So there is no more reflection, but the surface itself will start to emit radiation. So in this case, I want my surface to minimize or to emit as less as it can to reduce the losses by emissions. This is actually the concept of the selective surface. You can read it here. It is desirable to have long wave emittance of a surface as low as possible to reduce losses. As I said, the surface, just look at this blue one and imagine this one is a surface at 400. So it will start to emit from here. So I wanted to minimize the losses. So less emittance. Why we make this one, or what we call this part, we call it this wavelength, we call it cut-off wavelength. Why? Because the temperature, if you look at this figure, the temperature of the surface in most flat plate collector, as I said, is less than 400 Kelvin, while the effective surface temperature, which is the sun, at 6,000 will have maximum part. So both of the surface here, the surface or the collector, say, in the ground, and the sun will start, we can say, where we have overlap between this one, it will be almost in 3 micrometer, or we can say at less than 3 micrometer, because at 3 micrometer here, or 2.5 micrometer at this one, the sun, the surface start to emit its maximum. At the same time, the sun will start to, okay, there is emission, but it's not that maximum because the peak will be within this range. Okay, so if we use this when we said absorptivity equal to emissivity here, and we said we use the relation of the Kirchhoff law, we can find, or we can make the selective surface as you see here. This is the selective surface. As I said, I will try to put below the cutoff wavelength, which will be here below 2.5 or 3 micrometer, where there is an overlap between the surface in the ground and the sun. So below the cutoff here, I will try to make a surface with low reflectivity. Why? Because below the cutoff here, the sun here will emit its maximum, and the losses from the surface will be mainly by reflection. And as I said, the reflection depends on the incident radiation. So below the cutoff, we will try to make less reflectivity. Okay. Above the cutoff here, what will happen? Above the cutoff here, as you see here, the surface itself will start to make emission, to emit radiation. So in this case, we will minimize the emissivity of the surface, which means that if the reflectivity according to this relation, so the reflectivity can be high, no problem. Why? Because actually the sun here, it will start to emit less radiation. So here the reflectivity depends on the incident radiation. As I said, why we are playing with the reflectivity? Because the reflectivity is the only property that can be measured within the lab, or we can play with it. So we can make a surface, and this surface we coated, or we put on it a certain material to increase the reflectivity or reduce the reflectivity. And depending on the relations, this we already talked about it before, within the Kirchhoff law and other relation, we can control the emissivity and the absorptivity of the surface. Up to here, is it clear, the concept of the selective surface? Okay. All of you is fine? Mariam and Adil, Adnan is okay. Okay. So now let's see some comparison between selective and non-selective surface. If you see here, this is the non-selective surfaces or material, and this is the properties of the selective material. As I said, we want maximum absorptivity. So what we do normally if we just take a copper or any plate and we paint it with the black paint. So we know that if I paint it with the black paint, what will happen? I will have high absorptivity. So suppose that I have a surface and I just make black paint on it. So the absorptivity will reach 98%. However, this is not a selective material because this black paint is not treated to be selected. So what will happen? You will find that the absorptivity of it 98%, as well as the emissivity almost 98%, which means that all the radiation that already incident, it will be at the same temperature, it will be maybe emitted. So there is nothing from it. Okay, so here I have high absorptivity and high emissivity. Okay, this is for the non-selective material. If I have iron at a temperature 468 Kelvin, the absorptivity of it is 44%, but the emittance almost more than 10%, which means that I have a high losses of radiation due to emission. So if I'm taking my surface and I make or coat it with a certain material, we said black chrome material. With this black chromium material, we put it on a stainless steel or steel nickel on a certain surface. What will happen? We find that the absorptivity of it 95%, as you've seen here. I have high absorptivity, same like the black paint, high absorptivity, 95 or 98%. But if you see the emittance or emissivity of the surface, how much it is? It's less than 1%. But here, the emittance is also very high. So this is the selective material. If you compare the absorptivity and the emittance, you will find high absorbance and less emittance. To the properties or to make selective material, this is the property that should be, as I said, high absorptivity at a range of from 2.2 to 0.3 or to 2.5 or 3 micrometer, high absorptivity at a certain wavelength, which is above the cutoff wavelength, and low emissivity when the cutoff or above the cutoff, when the wavelength is more than 2 micrometer. At the same time, this is actually just as a surface and coated, or some material will be adhere on it. So we should have total adherence to the metallic substrate. That means it will be totally or well adhered or well coated within this one. This material at the same time should not be expensive, should be inexpensive and easy to apply to avoid the high cost which make the collector visibly not economically visible. Okay. Also, there is a here when we talk about the selective material and the coated here, we relate it to the spectral or to the wavelength. So we should have a good or there is no appropriate or the spectral transition. So I'm transferring or the transition from a short wavelength to the long wavelength, from ultraviolet to the visible, whatever. So we should have the spectral transition is upper, so there is no optical and physical properties are steady. So these properties are steady within this one. This is some of the properties of the selective material that should be there when we apply it to the surface. The selective material, the concept of it, is it clear? So now I'll talk about the other thing here. We have the angular dependence of solar absorptivity. Always, if I want high absorptivity, we compare the absorptivity depend on the incident radiation. So the directional absorbance of a solar radiation of ordinary black-ended surface is function on the angle of incidence. So this is, say, you see this one, flat plate collector, and the angle of incident is almost 0. So I have totally high angle of incident or high cosine, which means, if you remember when we talk about the tracking surface, we said it's have high cosine, with cosine equal theta equals 0. So the incident angle here or cosine, the incident angle will be higher. We're going to try to make it perpendicular. So here I have flat plate collector. When the incident radiations here is normal to it, we will have maximum absorptivity. Okay, when we change the incident angle, there is change in the radiation. So there is a relation between the average absorptivity of the surface to the normal absorptivity depending on the incident angle, which we have alpha here represent the average angle for the real surface or absorptivity of the real surface. Alpha n here, the absorptivity of the surface if the radiation or incident angle is maximum. Okay, so the relation between them, or the ratio between them, depending on the theta. This is the equation to find alpha over alpha n. Alpha here, the average, which we are going to use it later, and we're going to return to this one when we talk about the flat plate collector. Just you have to see this graph. I'll just make it bigger. Okay, so this graph showing the incident angle and the ratio between the absorptivity of the surface to the absorptivity of the surface if it's at normal or normal absorptivity. So if I have, say, the incident angle 60, then the absorptivity will be, say, 82 or 80 something. If I have the incident angle 20, what happened? I will have more absorptivity. So incident angle here, whenever we are increasing the incident angle from 0 to 90, what happened? The absorptance will be reduced. This part, we're going to return to it again when we talk about the, when we go to chapter 4, flat plate collector. Yes, Omar?
Doctor, is this phenomenon specific for flat blackened surfaces? I mean, what about other surfaces? Do the absorptance change with the angle of incidence?
No, all the receivers. It's not
Or receivers.
Yeah. This is just example. I make it for the flat plate collector, but actually for all the receivers.
I mean, what about like a normal house, like material maybe on the roof? Does it always like change the? Does the absorptance change with the angle of incidence? With the solar radiation?
Yes, because if it's not always, even if the roof, if you have a building, say, you're just talking about a roof, normal building, yeah?
Yeah.
So when the sun is perpendicular or normal to it, because of that, it's take highest absorption. Because of that, the material of the roof itself will make absorption for the radiation and it's have high temperatures. So normally, if it's the roof so tilted or there is some, because of that in the roof or the building, in the afternoon, mainly in 12, they have high absorption because the radiation almost or the sun is normal to the sun, to the building. So also if you are making the surface tilted, some of them, they're making the roof like this. So sure, it will reduce some of the, so it's general.
Yeah, general. Okay, thank you.
Okay, welcome. This is regarding the dependence of the angular dependence of the solar absorptivity. So now what we have already covered, we have covered, just I make this one back, okay. So we have covered for the absorber. You remember when I started talking about the equation, relation between reflectivity, absorptivity, and transmittivity, what I said? I said for opaque surface. Then I put tau equal to 0. So that's mean finding the property for the absorber, okay, which mean the reflectivity and the emission or the absorptivity. So if we have a collector, what we have in the collector? Actually, the component of the collector is number 1, we have, then we have the absorber. So this absorber already you cover it. Now I want to talk about the cover, the transparent cover. So what we have in the transparent cover, we have the most important property, which is the transmittivity, tau. Okay, so the next slide here, I will talk about the transparent plates to find the property, which is the transmittivity of this surface. If you remember always when we said a glass, we said a glass with transmittivity, say 0 or 88%. Why we don't say 100%? It should transmit all the radiation, but it's not. Why? Because some of the radiation will be considered as losses. So I want to find from here the losses, which as Omar said, we have losses by reflection and absorptions. So I want to find these losses by reflection and absorptions and to find the transmittivity or the retransmittivity of the surface. Okay, we'll start just by general things here. I don't this equations one place. Which equation was? Okay, can I just finish this part? Then we go to the questions. Okay. Okay, if you don't mind, just because I want to continue this part. Okay. So here, this is the transparent plate, okay, and this is the cover. What will happen here? I have incident radiation, incident beam on the surface. When it's reached the surface, what will happen? Part of it will be reflected, and the incident beam will come with a certain incident angle, say θ1. So θ1 here represent the incident angle for the solar or for the sun ray on the surface. Part of it will be reflected. So this reflected beam will reflect it, as you've seen from this graph, it will be reflected with the same incident angle. So here I have θ1 equal to the same, theta here equal to θ1. And part of it, what will happen? It will be transmitted. While it transmitted, what will happen? It will be refracted. It's refracted toward the perpendicular, which will make an angle θ2 here. Okay, so the beam radiation, when it strikes the transparent plate with an incident angle θ1, part of this radiation will be reflected, this one, and the remainder, what will happen to it? It will be transmitted. While it's transmitted, it will be refracted, this one, or bent towards the perpendicular with an angle θ2. Okay, so θ1, which is the incident angle, and θ2, which is the refracted angle, are related to each other by the refractions index N1 and N2, which is from a certain media to another media. So it's here from coming from the air to the air here within this interface, or air to water, air to whatever. So there is a different refraction angle. So here N, we defined it is the refraction index equal to N2 over N1. N's here are the index for different media, and sine 1 over sine 2. So this, which we call it the relations between the two angles, which we call it Snell law. Okay, this refraction beam, this is what I want to calculate it, which we call it the losses by reflection, the losses of radiation by reflection. So this reflection beam have two, from media to media, have two components. One, losses in terms of perpendicular component, and I have a losses in terms of parallel component. This is actually type of physics radiation when it's come polarized and impolarized. So it's part of physics. I'm not going to go in deep to it. Just we can go to that. We know that this R1 and R2 here represent the reflectivity of the surface. You know that any property R, reflectivity of the surface, defined as the incident radiation, reflected radiation over the incident radiation. Just I make it more clear. Okay, I'll just make it bigger. Okay, see this figure? Okay, here what we have, I have here, this is the incident radiation. It's coming totally from the sun, 500 whatever. Part of it, it will be reflected, IR. So depend on the reflectivity. So R here, reflectivity defined as the reflected radiation, say this is 500, reflected 300, so that means 300 over 500, or IR, which is the radiation that reflected, over I, which is the radiation that incident. Okay, so here R, the reflectivity of the surface, defined by IR, the radiation that reflected, over I, the radiation that incident. And this is equal to the average component of the two components اللي هي reflected radiation on the perpendicular plane plus the reflected radiation on the parallel plane over 2. So R parallel, R perpendicular plus R parallel over 2. R perpendicular and R parallel, as we said, it is the two components of the radiation that already reflected. As a function on the two equations we talk about them, the incident, the two angles, sorry, I talk about it, the incident angle and the reflected angle. So R bar, R perpendicular, equal to sine square theta 1, which is the refracted angle, this one, minus theta 1, which is the incident angle from the sun, over sine theta 2 plus theta 1. And this is the parallel component. So this one, the first part, which is the reflectivity calculated at an average perpendicular of the parallel component. This is if I have the radiation incident on the surface with an angle theta 1, whatever theta 1 equal 30, 20, 50, 60, whatever. Type. If I have the incident angle, the radiation incident perpendicular like this, which means that theta 1 equal to 0. So if it's coming like this incident normal, and then it will be transmitted normal, which means that the incident angle theta 1 will equal to theta 2, both angle equal to each other, theta 1 equal to theta 2, because always when we said the refracted radiation tried to bend towards the perpendicular. So it's already coming perpendicular. So theta 1 will equal to theta 2. Both of them are equal to 0. So in this at normal incident, both angles are equal to 0. In this case, I'm not going to use this equation. To find the reflectivity, I'm going to find it in terms of the indices N1 and N2. So R0 represent at normal incident, both angle theta 1 equal theta 2, or we can say R perpendicular equal to R parallel. So the reflectivity equal function on N, N1 minus N2, N1 plus N2 over square. Okay, so this is the first part, or normal information, or normal about the transmitted radiation and the losses due to the reflectivity. Let's apply this one to our cover, glass cover. This is the glass cover. Okay, I have, this is the glass cover. Always the glass cover, it's have a very small thin layer, this one, slab. Okay, so in the solar application, the transmission of radiation is through a slab or a film of the material. Whatever it will, there is a small thickness. You can just consider it as a thickness, whatever this thickness. Okay, so imagine this thickness. You see the red circle here, I do it. I have surface 1 here and surface 1, 2 here. So this is the surface. This is the first surface 1, and this is the second surface here. What I have the incident radiation coming from the sun, total. So it will be without any losses. So it will equal to 1. So this is number 1, which represent what? Represent the total radiation. When it reaches the surface, first surface, this one, what will happen? Part of it will be reflected, R. Part of it will be reflected here, R. The other, what will happen? It will transmit it and reach the other surface. Now this is the other, which, so the transmitted will be what? 1 minus R. 1 minus R will be transmitted and reach the other surface. Okay, so when it reaches the other surface, which is here, what will happen? The same story. Part of it, it will be reflected, which is here. This is will be reflected. So the reflected equal to what? 1 minus R time R. R is reflected. If you remember the equation, R equal to IR over I incident. So the reflected here equal to R times the incident. So the incident 1 minus R times R. Clear? So part of it will be incident, will be reflected, and part of it will be transmitted. So the transmitted equal to what? 1 minus R minus the reflected, the incident minus reflected, which means that 1 minus R is 1 minus 1 minus R times R. This is equal to this one, which is 1 minus R minus 1 minus R times R. This one. Okay. When it reaches this point, what will happen? So it's coming here. Part of it will be reflected, part of it will be transmitted, and so on. When it reaches this part, also part of it will be reflected, part of it will be transmitted. So the transmitted here, summation of all the radiation that transmitted will equal the transmitted radiation after losses by reflection. Is it clear, or should I repeat it again? Okay, so if I go here, now, as I said, the here inside, which is already transmitted, now it's already leave this part and start to transmit it, is equal to the summation of the transmitted radiation after losses by reflection. So this is the first part. Okay, so tau perpendicular here, or tau here, represent tau R here. This will be the same for both the parallel and the perpendicular component. So here tau R represent what? Represent transmittance. Tau R is the average of two components, which is mean that the transmitted radiation after losses by reflection. Okay, so this is first part. If I have more than one glass, sometimes we have more than one cover. Glass, if this is the glass number 1, this is glass number 2, then I have the absorptance, which means that when it's happened all this story within the glass 1, within the slab of the glass 1, then it reached glass 2, again I will have the same story with the glass 2 before it's reaching the absorptance. So here it depends excuse me it depends on the number of the covers. So if I have more than one cover, I will add it as n. So this equation the same here. N here represent the number of covers. If I have one cover, 2 minus 1 will be the same equation previous. If I have 3 covers, so I have here n equal 3, so it will be 6 minus 1. So n here represent the number of the covers. This equation again represent what? Represent the transmitted radiations after losses by reflection. This is the cover. I have losses by reflection. But as you see before, I told you this is a thickness. And always we know that if I have radiation incident on a surface, part of it will be absorbed by the surface. Whatever this surface, black surface, transmitted surface, there is an absorption of this radiation. Okay, so there is another losses due to the absorptivity of the surface. So the other losses depend on what? Depend on the type of the glass and on the thickness of the glass. If I have high thickness, that means it absorbs more. If I have clear glass, if I have glass with texture, if I have glass brown, which means that it will absorb more. So this is which we call it the two parameters, the extinction coefficient, depend on the glass quality and the thickness of the glass L. So tau alpha here, or tau A, whatever you want to call it, represent the transmitted radiation after losses by absorptance or absorptivity of the glass, which is function on the K, the extension coefficient will be given depending on the glass quality. I have a very high glass quality. When they make it, they try to make it very pure. I have some glass that still have some impurity, which make it can absorb more. So this is which we mean by extension coefficient. And L, which means the thickness of the glass. I have a glass of 6 millimeter, I have glass of 3 millimeter, whatever. And on the theta 2, which is the refraction angle. Okay, so now I have the transmittivity. I can find the transmittivity of the glass tau, which is equal the transmittivity due to the reflection to tau r time the transmittivity due to the absorption or after losses by absorption. Tau, this is what we already give to you in the problems. I said a glass with 0.88 transmittivity or 92 transmittivity, which means that we already calculated the losses by absorptance and by reflectance. So tau here, to find the transmittivity of the glass, you have to find both part, then multiply together. The product of it will give you the transmittance or the total transmittance for the glass. Okay, which is already, I will show you here. Sorry. So the total transmittance, considering both reflections and absorption, equal to tau A times tau R. Okay, you know how to find tau A now already, and you know how to find tau R, function on theta 1 and theta 2. And if I want to know also the absorptivity of the cover, it will be alpha 1 minus tau A. This means that how much or what is the absorptivity of this glass or the graph, and what is the reflectivity rho, which is equal tau alpha minus tau. Remember, absorptivity, this one, and reflectivity here related to the cover. Related to the cover only, which means the property of my cover. It's not related to the absorber. We already talked about the absorber before, okay, in the previous lecture. Now I'm only talking about the cover. So the cover here, it can, now I'm talking only about the transparent cover. Before we said opaque. Here I'm talking about transparent. So for this cover, I can find the transmittivity of it, and I can find its absorptivity and how much it will reflect, reflectivity. Okay, so this is the property of the cover, how to find it. Is it clear? Before going to the example, I think Muaz, someone asked questions. Can you please repeat your questions? I just, before going to example. What was your questions, Muaz? Yeah? Slide 54. Which one? I'll just go back and stop me. Okay. Which one here? This one? Yes, Muaz. What is your questions? You can talk, Muaz. It's to save the time. The equation. Okay. So this equations is relate the absorbance for the surface to the absorptance of the surface if the incident radiation or the radiation was normal. This is absorptivity of the surface to the absorptivity of the surface if the radiation was normal. So alpha n here represent the absorptivity of the surface if the sun ray is normal. This is the optimum. And alpha here represent the absorptivity of the surface function on the incident angle. Okay, so it's not for flat plate only. As I said, it is for any absorber, any surface, when I have incident radiation on it. But normally we use it for our collector. So it is for absorptions here, for the, also later when we talk about CSP, we'll also talk about this one the same. So it is for any absorber that will absorb. I'm talking about absorptivity. So any surface that will absorb from the sun. You can just take it in general like this. Okay. Or even if it's changed the tilted angle. Yeah, if you change the tilted angle, yeah, later if you change the tilted angle, then you will have equation that you will see it later. If we talk later when we talk about the ratio between the incident angle and the tilted angle. This is almost after 2 lectures. We'll talk about the radiation. Then you can relate these together. Also, if you go to the, when I talk about the measurement, I think there is a figure I have already included. You can see the relation between the incident angle and the tilted angle. Okay, thank you. Okay. How much is the typical value of the transmission for the collector? Just 1 minute, I see your question. Transmission of the collector glass depend on the glass, yeah, Omar. The transmittivity depend on the glass, as I told you. If it's clear, if it's made, when it's made, there is extension coefficient on it. So transmittivity depend on the material itself. Whenever you go for higher material or high quality for glass, you will have a certain transmittivity, even when you make it. So depend on the material of the glass. Each glass, different transmittivity. Depend on the quality, actually. So if you want it, for example, if I want it, say, for example, if I want it for building, so I'm trying to minimize the transmittivity. Sure. So in this case, I'm trying to have more, I have to certain, I'm going to have extension coefficient more or less depending on the absorption. So transmittivity, it depends. From for building, I'm trying to make it less as I can. If I can, I don't have a figure actually, but if you have it less, say 10%, it will be fine for building. But for solar application, it should be high because I want more transmitted. So depend on your application, ya Omar. Did I reply to your questions? Okay. So sorry, I'll try to go to the example. Okay, so this example for the same or in the glass, it's direct one. Just we have to do it together. I will be grateful if you start to calculate it with me, or someone volunteer and solve it with us. Who's volunteer? Not Omar and not Muaz. I want new faces, new voices. Okay. Abdurrahman, Adnan, Ali Umran, Alia. Any volunteer? Participating is very important. Okay, Adnan, thank you. So can you start to read it and just let us to know how it can be solved? It's direct one. Just please use your voice.
Doctor, you want me to read the question?
I want you to start to solve with me. Okay, just read it and explain it, and just tell me the procedure, how we solve it. Adnan. while you are
Yes,
disappearing?
I'm reading the question.
Let us hear your voice.
You want me to read it?
Yes.
Okay.
Yes, we have to hear. Okay.
Solar energy collector use a single glass cover with a thickness of 4 millimeters. In the visible solar range, the refraction index of glass N is 1.526 and its extinction coefficient K is 32. Calculate the reflectivity, transmittivity, and absorptivity of the glass sheet for the angle of incidence of 60.
Okay. You start to find what? The first one is required to find?
Reflectivity.
Okay, so what is the reflectivity? How we can find it? Reflectivity.
It is
Equations already here, by the way. I write all the equations. Don't go to your slides.
reflectivity.
So if you see here, the reflectivity of the glass is 1. I'll just show you here. Reflectivity equal to tau alpha here. What does it mean? Tau alpha. Transmittivity after losses by absorptance. Okay, tau alpha. And tau here, what's mean? The total transmittivity. The total transmittivity. Okay, so I want to find the reflectivity. So directly we go to the equation here. This is the reflectivity of the glass. Again, please do not confuse or mélanger, what do you say? Making both equations, mix both equations. Okay, so here rho transmittivity, which means tau alpha, the transmittivity after reflections by absorptions, minus tau, which is the total transmittivity. This is all for the glasses, all these equations for the glasses. Don't mix this with the other equation, which is for the absorptance. I'm talking about transmittance. Okay, so rho equal tau alpha, which is depend mainly on what? As we said, on the extension coefficient K and on the thickness of the glass and theta 2 type. So I will go directly to this equation. K, what is K, Adnan? It's given to 32.
Coefficient, yes.
Yeah, 32. And L is the thickness, which is equal to what?
4
4.
millimeters.
Type. Cosine theta is what? Theta 2 is what? The refraction angle or the incident angle? Theta 2 is what?
60.
Is it given? Wait, ya Ali. Is it given, ya Adna? Okay.
Yes, it's 60.
No. 60 is the incident angle, which is theta 1. Okay? So theta 2 is the refraction angle. طيب. Thank you, Omar. Adnan. Another one. How we find theta 2? It's not given. How we find it? We have, yes, Amna, we have already the ratio between the incident angle here. So we're going to find n already given, 1.56 equals sin theta 2, theta 1, already given, incident angle, over theta 2, which is, this is what we want. So I'm going to use the first equation, n equal n2 over n1, sine theta 2 over sine theta 1 over theta 2, and I find theta 2. Again, remember, tau, which is that tau due to the absorptance, function on the refraction angle, not in the incident angle. Okay, so this is, I find from here, theta 1. So we'll see n, yes, Omar, 34.5, thank you. n equal n1, n2 over n1, and we'll find theta 2. After I find theta 2, I think everything will be clear. Then I can find the reflectivity rho. This is the first part. The second one, I want to find what? The transmittivity. The transmittivity, the total transmittivity tau equal to the transmittivity due to the reflectivity tau r multiplied by tau alpha. Already I find tau alpha. Now I want to find tau r. This is the equation. Remember here what he said, single cover. So n is not included. If he said double cover, that means n will be 2. If I said triple cover, that means n will be 3. So this is not included here. N is not included because it is a single cover, which is only 1. So here I go to the equation. Tau. Okay. Yes, I found tau r. Tau A. Yes, Omar, thank you. It's right. Tau r, we find it. Okay. And we find tau. Multiplication of both numbers, I will find the total transmittivity. Then the absorptivity here, which equal 1 minus tau alpha. Is it clear? I will be grateful if you solve it. The solution is, or the answer is already sent to you, I think. It's already in the slide. Just solve it and find the number. Maybe something wrong. Okay, we are human, so sometimes maybe I have make something wrong. So you just try to solve it. Okay. And also you can practice. I wrote it here. For the same problem, calculate the reflectivity, transmittivity, absorptivity, but here for a glass sheet of a normal incident angle. Remember when I said normal incident angle, which means that theta 1 equal theta 2 equal what? Equal 0. So we are going to depend on the incident, on the reflection indices. I will stop until here. And if you have any questions, please ask. I will stop EV recording to minimize the time, the load in the PC.